Okay, welcome back. This is the continuation of the video on the home dome or the dome home project. And again, this is the 64th iteration of that design. I decided to push forward even though I found some issues with the model. Some minor issues at that, some layering issues that I will push forward with because I really right now don't have the full version of AutoCAD. This is just a DWG viewer with very limited functions, AutoCAD functions. And for the sake of time, I will go ahead and push forward. This is the model again, showing both the first deck floor panels and the second deck floor frame. As you can see, these are 2x6 pieces or members, lumber, and the ones that are on top that are overlaid on top are 2x4s. Again, 2x4 not being the exact dimensions. As I mentioned a few times, I won't bore you with the real dimensions, which are 3.5 by 1.5 inches. So this is the floor or ceiling frame, as whatever you want to call it. And of course, these panels underneath are the ceiling for the first deck, the ceiling panels. Again, these are 8 foot by 4 foot or vice versa, planks of plywood or any other material that you deem replaceable, similar, or better to use in this application. Over here in this center area, we see right in the middle by the center column a platform made up of many 2x4 members backed by 2x6s. Again, 2x6s being 1.5 by 5.5s. That is the design, and we have about 1, 2, 3, 4, 5, 6 of the 2x6s running along in that direction. Why so many? Because that again is a bridge that requires quite a bit of support, vertical and horizontal especially. These 2x6s are attached to that column or pillar right there, securely bolted to the center pillar as well, to this pillar, and to this pillar. Not to mention this pillar as well, and that pillar right there, which you cannot see so well from that angle, so let me change the angle. And the pillar I was mentioning is that one right there, about near the center of the screen. Again, all of these pillars are attached to the floor or ceiling frame, securely bolted, if not bolted, braced with appropriately sized alloy deck screws. Same here in this area. As you can see, these 4 members come in contact or are in junction with that pillar. The pillar, of course, is not penetrated. The members themselves are cut flush with the pillar and securely attached perhaps bond it with some sort of long-term cement. Again, these members are securely attached and braced to provide support for this entire frame. All of these pillars provide support for the frame. They basically stand alone. They really, if done right, if secured right, really don't need any other support to basically stand for a normal weight, I would say average weight individual to be standing on this corner. Would not need any other support than the one I just mentioned, fastly secured or securely fastened to each point of those. Of course, you would have to keep these members whole that entire run. Right here is a whole piece securely fastened to each of the pillars. This run is preferably also an entire piece from this point to that point, and I may consider changing that to run an entire run from end to end. That is another thing I will be changing. That way that length of lumber is not interrupted, therefore providing much more support. Perhaps a steel truss can be put in its place and provide attachments in as many pillars as possible, perhaps 3 in that case. And the same would apply to this member right here, horizontal member. Very long run, perhaps of close to 30 feet or even more. And the same would apply to a vertical member, a horizontal member that I think I may need to add right here. And again, being attached to as many pillars as possible. I think there is a member that already does that. I believe that one, but I need to ensure of that. I cannot really see it from this angle. Let me change it. And again, excuse the low quality and the slow reaction of this software. I'm working with very limited hardware and software. So this indeed has a member that runs the entire length right here, attached to 1 and 2 columns or pillars, as I call them. This run right here, of course, is also one that is attached to this 2 pillars and braced to that one. And I will probably be thinking of making this an entire run, a continuous run. So let me take a note of that. I'll be right back. So basically these are right here, 2x4s here in the middle, in the bridge area. This is basically the floor or platform of the bridge. These are, again, the bottom ones are 2x6s, and these top ones running from your left to your right, more or less, are 2x4s. Again, the 2x6 in this center pillar being attached to that center pillar. and that is the ceiling panels plus the floor frame for the second floor. So we'll turn on the panels for the second floor. These don't show the paneling divisions as they should on the as they show it on the bottom side. So I will take note of that. And show those divisions. I like doing that because that gives it a lot more information. Again, being a BIM or BIM design, building information model, you want to give it as much information as you can, and that would give information about how many panels it would be required to build this structure. As you can see on the bottom, each panel is seen, so you can count and estimate how many panels will be used. Estimate cost, estimate labor, estimate all kinds of stuff. So we'll throw one together with this. We'll throw on a few more layers to show what the interior frame will look like once built. So the interior frame for the second floor and for the first floor, which I call decks. I call them decks again because this building structure is more in line with that of a ship, such as a submarine or a naval vessel, more than just a structure that sits there and is on life support, as some other people may say. This structure is being designed to be self-sustained in not only structurally but also in utility, also in utilities like water, sewer, and energy, as far as electrical and heats and cool air. It's all going to be self-sustained. It's not going to require any kind of exterior connection. So this is right here the framework of the interior. Again, it is designed or being designed to be, of course, is a working project, being designed to be entirely self-sustained or stand alone. By that I mean it doesn't require, should not require the exterior skeleton to support it. As you can see, there are many columns shown in orange or dark orange or red for the main columns or pillars. And of course these green or yellow members going across are just the support for the columns. They really do not bear too much weight, but they do add stability and rigidity to the entire structure, not to mention the utility of them as being members that add to the structural integrity of the entire design or model. Of course, more can be added. As everything, there's a limit, upper limits, dealing with cost and dealing with time taken to build, and necessity. I believe these are the basic members needed. Of course, you can add more. I would highly not recommend taking off and using less for the sake of saving perhaps time and money, because I believe you will be deducting from the entire building's stability. And just to show how the building could really stand on its own as it is shown right here, let me show you a few other views. This is a more perspective view, more as your eye would capture it in real time, real life. So as you can see, the entire first floor, or this floor area up top, you can stand at any point and be supported by vertical columns, some major, some minor, meaning some small, some larger. Like if you were to be standing right here in this corner. Let me turn on the human reference that I have to give you a insight or perspective of what a average size human would look like inside of this structure. I do have a rendering or a series of drawings that showed just that, and I call it human reference. And here they are. I use these mostly for showing a reference and also to accurately put views or cameras, as I will show. I have many different views as seen from the perspective of a person, and that person is shown here. Unfortunately, I only have a few up top that none of them are here in this area, open area. But back to my point, you can stand anywhere on this floor area and be supported, well supported by vertical columns. I will show you a view from the side that shows that a bit better. And there it is. This area right here is probably the one with the least amount of vertical support. This area that I'm showing right here. The software is blinking just a bit. We should stabilize this area right here. Probably the one with the least amount of vertical support again. But this, however, is not a problem. This floor area is being designed to attach to the exterior skeleton. These trusses here, and I will show that here next. But to give you a view of the other supports from another side. This area, the center area mainly, is well supported on this end, on this side, by vertical columns and pillars. Again, all to be attached, securely attached to the floor frame on the second deck, as well as the first deck. Another corner view. This is the northeast. That's why I put those large letter indicators there, so they can be easily identified. Put them on both plans, the vertical elevations as they call them, or side view, and also the plan view, so it can be easily seen from each of those views. And as you can see, plenty of vertical column support for the floor. The floor on the second deck. Of course, the floor on this first deck is supported by the concretes, both the concrete arrays, circular or perimeter array, and the ones on the inside, the square feet or bases. As you can see, I went over that on the, I believe it was the last couple of videos. So that shows you there that there is plenty of vertical supports. Of course, I may decide to add some more here when I finally get the software running, the powerful and all important AutoCAD. I've been having to run free trials here repeatedly, and they have finally caught up to me. Autodesk has finally caught up to me and has started relentlessly and continuously denying for me to run any more trials. So I really cannot afford their software. However, I am a AutoCAD operator, and I really need to have a copy of it, a legal copy of course, to make these very important changes and improvements. So let me take a few notes. I'll be back. Thank you. Okay, welcome back. This right here, I have turned on the layer for the what I call the strut braces and the struts, which make the framework, or the skeleton as I call it, for the dome. So here you can see the dome itself starting to take shape from the outside. This is considered already part of the exterior. These red, represented in red, pieces or members, I call them struts. They are nothing but 2x4 members of a certain size. I'll have their dimensions, exact dimensions, in the plans, in the drawing documents that you can freely look at. And why did I use these instead of just using a whole piece curved and all that? Because again, this structure is designed to be built with the least amount of materials for one, two, with available materials for two, and three, with the least amount of labor and skill. even one person is conceivably able to put this thing together. That's how I planned it. So these are basically pieces or cut members of lumber. Could be lumber, but more preferably some sort of composite material that it's stiff and sturdy, stiffer and sturdier and denser than wood. But it could be a high quality type of wood. These will provide the arcs that I'm looking for in the design. The basic concept of this design is the use of a series of arcs, ovoid elliptical arcs, and I will show you what I mean here in this view. As you can see, if you focus on the last or the very extreme sides where I'm pointing at, this arc, that is basically what it is, an arc, kind of like the St. Louis arc. An elliptical arc, it's among the strongest, most stable, and structurally sound shapes and objects that you can find in nature. Think of an egg, think of many other shapes that resemble an egg, and this is what this is: an oval, ovoid, or elliptical arc. And it's not only an arc, it is a array of arcs. It is a series of arcs revolved around a common center, as I will show here. From the top, a plan view, that is what it looks like. And I believe this to be among the most stable, again, and structurally sound buildings you can basically put together. Oh, but you say there are only, out of all these arrays of arcs, let me see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 arcs. Complete arcs, but there are only 4 arcs that you say are completely made, or they are basically going into each other's opposite. They complete or mirror each other. And if you look at this, yes, that's true. But there will be another structure here that I will show that basically distributes the support among all of the arcs that are not completed or not mirrored or not sharing another side, an opposite side, like this one is not sharing an opposite side as this one just yet. But once I put that circular or circumference shape or structure and fasten them up securely, with bolts, it will transfer whatever forces among the entire structure, and I'll show you that here, what I mean. But even without that, even if you did remove the arcs that are not touching the opposite end of the arc, it would still be a sound structure. I believe this is the center column or center pillar with these members attached, which are in turn attached to each strut, as I call them. Each strut is again secured to the strut below and the strut under it via bolts. And I have a certain arrangement of those bolts, which are to be flushed on one end, at least flushed with the strut, going through both of the struts and securely and almost permanently bonding that strut to the other. Of course, you can use certain type of cement bonding material to make that bond even stronger. And I will go over what these are here momentarily. So that's the array of struts. I believe they are about close to 3 to 4 feet. If I have to, no, there are more like 2.5 foot, 2.5 feet, if I remember correctly. But do refer to the drawing documents for exact dimensions again. And they are arrayed in the fashion shown, of course, equally spaced and attached all the way to the very top of the column right there. Securely fastened, very strong, very sturdy and durable, yet flexible and giving structure. That is what you want, a giving, and somewhat flexible, semi-flexible structure. You don't want something rigid that will crumble with a little bit of shaking of the ground. You want something that gives a little bit. So these gray appearing pieces here, or twins, are braces. These braces are triangular in shape. They are uniquely dimensioned for each rank or each row, whatever you want to call them, you know, going from top to bottom or bottom to top. So these two, each one is a different dimension. Each one on each row again. So these two are the same dimensions. These two are the same dimensions, but not these two. Now these are not the same dimensions as these, but they are the same dimensions as these, and so on. As you can see right here, this is a perfect example of how the inside is braced with the skeleton and further supported. The skeleton itself is further supported by the few of the junctions. There aren't many, but there are enough to provide more. Like this one here could be one. There are many to support and provide more stability to the entire structure, not only the outside but the inside structure as well. And I will turn on a layer that will show you exactly what these braces are for, but before I do that, we'll analyze the bottom struts, which are very important. They provide a way for the actual framework or the skeleton to be attached to these belts here that I mentioned earlier that go around the perimeter and are stopped from expanding or spreading by these bolts that go around the perimeter as well. But these struts are cut in a way that they will have a narrow slit that they will slide right into these wooden or composite or metal belts. Again, these struts could be made of wood, could be sourced from a some type of aluminum or lightweight alloy or composite. I mean, whatever suits for the construction. As you notice here in the entrances and exits, the belt does not go the full height. It is cut to the dimensions shown on the drawing or the construction plans as such, and this is to be flush with the boards, the floorboards. This cut will make this flush with the floorboards and get it ready for the building of the entrance doorway, door frame on each end, the south and the north, as shown in this drawing. Of course, this doesn't really have to match the construction site, these cardinal points, but I have them as reference here for purposes of analyzing the drawing, the model. So this is the entranceway, this right here, and that's why they have double struts. I may have to and will copy those to each one of those as well. So we'll take note of that. Again, I am improving this design and model as I go. Okay, so I'm back. So that is that. The bottom struts are very important, and the way that they are cut, very important. So taking note of as I go, I will have to get rid of that cut right there. That this should be a whole member. Again, making improvements as I go. This is a working model. I have been working on this for many hours, perhaps hundreds of hours now. So moving on to why these braces are there. And again, side to side stability and integrity is not so good right now as those arcs go. As far as those arcs go, you can stand in between those two arcs and push them apart and they'll bend like rubber band quite easy. Not to take away from their integrity, as if you were to push them back and forth into and out of the center, they would be a lot more rigid. But to fix the instability or the lack of rigidity from side to side, I went ahead and developed that system. That system is original. It's an original design. Very easy to build, I believe. Very easily sourced for the material. The material should be, I believe, a composite. I would not recommend wood, but however, it could be also be made of very high quality and dense wood. But I would recommend materials such as composites or even a type of metal, lightweight alloy, if these struts are made with alloy or sourced with alloys. So, just to show you my answer to the stability issue. So there is horizontal belts all throughout. These belts are to be fastened, securely fastened, perhaps using screws, adequately sized screws that go all the way through and through the braces, not necessarily the strut. You don't want to go through the strut because you'll have a ugly and dangerous and damaging point, sharp point sticking out from the other side. So you want to bore. I will have a pattern, recommended pattern to bore through and through each of these struts, and basically use adequately sized screws, deck screws, preferably, or something similar or better, to penetrate these and secure them. Of course, it could also be sealed and glued or bonded with high strength, high flexibility, high durability, long-term adhesive or cement. And you would do that in each and every location. This would require a certain amount of skill for accuracy and to perform this in a timely fashion. But it is quite possible. These belts here are designed to be made from wood, but not necessarily so. They could be made of other materials such as composites and even alloys that will take the shape. The most important thing is for the material to be able to be bent to shape as such without much energy use or without much labor intensive or equipment intensive methods. And just to change the view so you can have a better idea of how the belts would be placed, this is how they would look from as viewed from the side. Why, you say, they would have, I know the triangle on the inside supports the belt itself, so what is the triangle on the outside, you would ask? And the answer to that is the following. The triangle on the outside is part of the structural support and integrity of the whole arcs. The arcs are not done yet. The arcs have two parts, the struts and another piece that goes on top, and those pieces are the overlays, the frame, what I call the frame overlays. And they're nothing but pieces of either wood or composite that provide the surface to attach paneling. You want a surface to attach the outer paneling to. And this provides that surface. And not to mention that it also provides strength for the arcs. And if you cannot see here in the dark brown, here, these are those surfaces I speak of. They are nothing but 4 inch by 1 inch, so 4 inches wide by 1 inch deep, and of course they would be equally sized in length as such. If you can't tell really much by this view will fix that for you. This view tells you exactly what those overlays are like. These are the overlays in orange here. And as you can see, they are very much attached to these triangles. Again, via a recommended pattern of screws, alloy screws of adequate size. Of course, that would have to be pre-drilled, pre-bored. And it would make, I believe, a neat and good looking and strong and durable and sturdy structure. This top ring, very important for the stability. It distributes the strength or the loads throughout the top of the structure. See these arcs that as of right now have no end or no attachment to the center, because they would just overwhelm the center with too many materials, too many members. So for example, these two on this quadrant, the weights or the forces that they bear would be distributed right here with this ring among with the others, the other rings or belts. They will be distributed among the others. They would share the load. That is a basic concept. When you attach the members, when you fasten them together in some shape, way, or fashion, they will share the load that each member bears. Of course, the place of attachment is critical, but this is right here, I believe it to be pretty close to optimal. However, it is not entirely optimal as of yet, and then I'll show, since that, I will show what remains here, what needs to be here to make this a very sound structure, and I will show that now. If I can remember the name, I will take a quick break and find that. I'll be right back. So I'm back, welcome. So this right here is the ring structure that I mentioned just before I went on break. This is an alloy structure or ring of very dense and substantial size and thickness. I believe it is a 6-inch tall or deep and about 2 inches or 1.5 inches wide, more like the standard size of a 2x6. which is 5.5 by 2 by 1.5, but it is made of alloy, some sort of high strength alloy. I'm yet to decide on its exact composition, but it should be alloy, it should be metal, I believe. Uh, it could be alternatively composite. Perhaps it may be a viable option to use composite, but it, however, must be a very strong and dense material so that you can attach and secure each and every one of these members. These members go right through this material, and that material should be able to be bored here for that member and go straight through and be bolted in place, not screwed, not nailed, but bolted, so you can securely take that member, which this should be a composite, for strength and durability, so that could hold on to that member like it's its own, like it is basically part of it. It must be fastened good enough to make this part of that member, whether through a combination of cement and fastening or by fastening alone and straight friction. This member right here, it must be fastened again to this ring in a fashion that, as you can tell, is quite easy to see and do. This must have that's something I need to basically design and draw out so I can visibly show a bracket that goes from top to bottom, that attaches on each side to the ring and to the to this structure here, to this brace, straight down through this whole member and bolt it. So there should be a bolt going right through with a bracket, perhaps alloy metal, that goes bolted to that, and then with a hole so a bolt could go right through that. And I really need to show that, visibly show it in the plans and here in this model, so that way there is no question what must be done here, because this is very important to be attached. It's very tightly and securely attached and fastened to this member, to this ring, so that it can share the structural load throughout. The same should be done to each and every one of these. Again, these being much simpler attachments, bolt right through, of course, being bored, pre-drilled with an adequate size hole, machine drilled, not spot drilled with a hand tool. It must be done with a machine or a bench press drill. Very machine like. So I will take some notes, be right back. Actually, I will leave this video right here. We'll pick it up on the next video. Again, this is the top ring structure. Very important, very critical part of the whole structure. And I believe it to be a very sound and strong structure. This series of arcs, ovoid or elliptical arcs, supported by a center. This again is to be steel or some other type of alloy. This center column that goes all the way down into the ground a few feet deep with a concrete pillar cast or footing. Very sturdy, very secure, and very stable construction and design there for many years and decades of use, perhaps longer. Thank you very much. I will leave it at that for now. We'll pick it up on the next video, and please join me on that video. Thank you.